Hello students, welcome to Online Maths Classroom. This is part 3 of your topic Relations and Functions, and in this part we will cover solutions of your NCERT exercise 1.3. So let us start with it. Composition of functions and invertible functions. Now in this section we will study composition of functions, right? And the inverse of bijective function. Bijective means one by not. Now consider the set A of all students who appeared in your class 10th board, okay? Right? So this is as per your book, it is 2006. So you can consider any case, any year. Now each participant appearing in board is assigned a roll number, definitely by the board, which can be written by the student in the answer script, right? And in order to have confidentiality, what they do, that board arranges to deface the roll numbers of students in answer scripts and assign a fake code number, right? So a fake code number is there instead of roll number. Now let B is subset of N, be the set of all roll numbers, okay? And C again is the subset of N, be the set of all code numbers, okay? So B means B subset of N is the set of all roll numbers, and C subset of N is set of all code numbers. Now this gives rise to two functions. F is mapping from your A to B, okay, and G is mapping from B to C. Given by F of A is the roll number assigned to the student A, and GB means the code number assigned to the roll number B, okay. Now you can understand from here that F of A means the roll number assigned to the student A, and G of B means the code number assigned to the roll number B, okay, because here we are talking about the code number which is assigned to a roll number. Now in this process, each student is assigned a roll number through the function F, and each roll number is assigned to a code number through the function G, okay. So from above example, it is very clear that each student is assigned a roll number through the function F, and each roll number is assigned a code number through the function G. Thus, by the combination of these two functions, each student is eventually attached a code number. Means definitely by the combination of this, each student will have a code number now, right? So this is like giving rise to some definition which is say of this kind, that if F is mapping from A to B, your function F is mapping from, you can see, from A to B, okay, and G is mapping from B to C. There's G which is mapping from B to C, okay. Then the composition of F and G, composition of F and G, composition of F and G, it is denoted by your GUF. Remember it. Composition of F and G is denoted by GUF, not by FOG. It is denoted by GUF, and it will be defined as a function GUF from A to C. Okay, it will be defined as the function mapping from A to C, and GOF of X is equal to G of Fx for all X belonging to A, right? And this example gives a very clear idea to the concept of composition of functions. Example number 18 says, show that if F is mapping from A to B, G is mapping from B to C, they are 1, 1, then GOF mapping from this A to C, they are also 1, 1. So suppose we take an element like, we consider for 1, 1ness like your x1, x2, two elements in the domain, and such that f of x1 equal to f of x2, then we need to show x1 equal to x2. So here we'll suppose GOF x1 equal to GOF x2. So like from the definition, it can be written as G of fx1 equal to G of fx2. Now if G of fx1 equal to G of fx2, definitely fx1 equal to ffx2, right? As G is your 1, 1. So again this implies x1 equal to x2 as your function is 1, 1. So my GOF is also 1, 1. Example 19 show that if F mapping from A to B, G mapping from B to C, it is onto, then G of F mapping from A to C is also onto. So given an arbitrary element Z belongs to C, C, take an element here. There exists a pre-image Y of Z under Z, right, such that your gy is equal to Z by definition of onto function, since G is onto. Further, for Y belonging to B, there exists an element X in A. Y belonging to B, there exists an element X in A such that Fx equal to Y, because again F is onto. So therefore G of X means it is G of Fx, which is your G of Y, because F of X is your F of X is equal to Y. So, and G of Y is your Z, which is equal to Z. Show that G of F is onto function. Definition number 9. It says F is mapping from X to Y defined to be invertible if there exists a function G mapping from Y to X. See, F is mapping from X to Y, then there exists a function G mapping from Y to X, okay, such that G of F is equal to Ix, okay. G of F is equal to identity function of X, and F of G is equal to I of Y, means F of G is your identity function of Y. Then we say G is called inverse of F and is denoted by F inverse. So means if F is invertible, then F must be 1 1 onto, and conversely if it is 1 1 and onto, then it must be invertible. This fact significantly helps for proving a function to be invertible by showing that function is 1 1 and onto when the actual inverse of F is not to be determined. Now theorem number 1 is, if F is mapping from X to Y, G is mapping from Y to Z, H is mapping from Z to S are functions, then show that HOGOF is equal to HOGOF. Okay. Now we have, firstly, to prove them equal, I have to consider one element with it. Okay. I have to associate one element with each side. So let us start with HOGOF of X. Okay. Take an element X. So see, I will open first this O outside and then the next two. So it will be like H times GOF of X. Okay. H times GOF X. Okay. Now this again, now open this O, it will be like HG of Fx for all X in X. Okay. Now second case is HOG OF X. Right. So firstly I'll take this O. Okay. So it is HOG Fx, and then I'll go for this O, so it will be H of G Fx for all X in X. That means the results are same, so HOG OF equal to HOG OF. Okay. Theorem number 2 says that F is mapping from X to Y, G is mapping from Y to Z. Right? Both are two invertible functions. Then your GOF is also invertible with GOF whole inverse equal to F inverse O G inverse. So you can remember this result like we have done in matrices also. EB whole inverse equal to B inverse A inverse. So it is to show that this GOF is invertible with GOF of whole inverse equal to F inverse O G inverse. It is enough to show that here see this F inverse OG OGO F inverse, okay, right, it is to be proved equal. So what is I need to show that if these two proved as equal, as this F inverse OG inverse OGOF, okay, OGOF, this is equal to IX, and GOFO, this F inverse OG inverse is equal to IZ. Okay, means F inverse OG inverse OGOF is equal to your identity function of X, right, and GOFO F inverse OG inverse is your identity function of this Z. Okay, so start with it. F inverse O G inverse O GOF, right? So see, your theorem number 1 says that F, it can be written as F inverse O G inverse, right, and I'll associate this G with it. OG, OF. Okay, OG will be associated here. Now again, it is F inverse O. Now associate these two, G inverse OG and OF by again theorem number 1. Now what is G inverse OG? G inverse OG is your I of phi. Okay, G inverse OG is your I of phi. So it becomes F inverse OIY OF again by the definition of G inverse, right? And it becomes your Ix. Okay, it is equal to identity function of X. Similarly, the second part can also be shown to prove it as identity function of Z. Now exercise 1.3. Let F is mapping from 134 to 125. G is mapping from 125 to 13, and it is given by F is 123541. G is 132351. Write down GOF. Okay, this is your A, this is B, and this is C. Right, F is mapping from, that means you can see A to B, and this is mapping from B to C. G is mapping from B to C. So GOF will be a map from your A to C. Okay, so GOF will be, A is your 134 and C is 13. Means we'll put elements from 134 and you'll get elements like 1 and 3. So what is F of this 1, 2, 3, 5, 4, 1 means F of 1 is 2, F of 3 is 5, okay, and F of 4 is 1. Similarly, this means that G of 1 is 3, G2 is 3, G5 is 1. And what is GOF? Now start putting the elements in GOF. So GOF of 1 is G of F1. What is F1 is 2. So what is G of 2? G of 2 is 3. So I'll get element 3. GOF of 3, the second element 3 we'll put. What is G of F of 3? F of 3 is your 5. So what is G5? G5, see from here it is 1. Okay, so I'll get 1. GOF of 4 is G of F of 4. What is F of 4? F of 4 is my 1. So G of 1, what is G of 1 is 3, right? So means what do I get? I get the pairs as at 1, 3, 3, 1 and 4, 3. Okay. Now number 2 is let FGH be functions from R to R, show that F plus GOH equal to FOH plus GOH. FGOH is FOH into GOH. Now what is the definition of equal functions? Says that two functions FG will be equal if they have same domain D, and Fx equal to Gx for all x belonging to the domain, right? So F plus GOH of x is equal to your F plus G of Hx. This is by the definition of composite function, right? Now open it like F of Hx plus G of Hx. You can write it as F of Hx plus G of Hx. This is by the definition of sum function. Now what is F of Hx? Can I write it as FOH of x and this as GOH of x? This is again by the definition of composite function. Now take x common like FOH plus GOH of x by definition of sum function for all x belonging to R, right? So it becomes your that F plus GOH is equal to FOH plus GOH. This is by the definition of equal functions. Now similarly for the second case, FGOH of x is FG of Hx by the definition of composite function. Now open it, means separate F, it becomes as F of Hx, G of Hx. We speak it as F of Hx and G of Hx by definition of product function. This becomes FOH of x, GOH of x. Again by definition of composite function, and this becomes FOH into GOH of x, that is again definition of product function, and this becomes that FGOH is equal to FOH into GOH. Question number 3 is find GOF and FOG if fx is mod x, gx is mod 5x minus 2. And similarly for the second case, fx is 8x cube, gx is x raised to power 1 by 3. So fx is your mod x, gx is mod of 5x minus 2. Now we know GOF of x is g of fx. Like who is fx here? G of mod x, right? Now changing your x by mod x in equation number 2. See from here. you have to change x by mod x. So it becomes your mod of 5 mod x. Okay, this mod is outside. So you have to change this x by mod x. So 5 mod x minus 2. Right? Now again FOG of x will be f of gx, like f of who is gx? Gx your mod of 5x minus 2. Okay. Now I have to change x with my mod 5x minus 2 in equation number 1. So what does it becomes? It becomes, see, this x to be replaced by mod of 5x minus 2. So it becomes double mod. Yeah, mod, one mod is for this mod x and other, the x is also is in mod. So it is mod of 5x minus 2, which is your mod 5x minus 2, right? Because if your t belongs to R, then t mod is always positive. And hence this double mod is also a number, which is your t mod itself, right? So GOF of x is mod of 5 times mod x minus 2 whole mod this, and GFOG of x is your mod of 5x minus 2. Similarly, fx is 8x cubed, gx is x raised to power 1 by 3. GOF of x is g of fx. Now fx is your 8x cubed, so g of 8x cubed. Now I'll change x by 8x cubed in my this g function. So it becomes your, in place of x I'll put 8x cubed. So it is 8x cubed raised to power 1 by 3. So it becomes your 2x whole cube raised to power 1 by 3. So it becomes 2x, as this cube root and this cancelled. Okay. And FOG of x is f of gx, which is your f of who is gx, x raised to power 1 by 3. Now I'll change x by x raised to power 1 by 3 in my function fx. Okay. So I'll get it as 8x raised to power 1 by 3 whole cube. 8 in place of x I'll put x raised to power 1 by 3, and its whole cube will give me 8x. So GOF of x is 2x and FOG of x is 8x. Number 4 is my, if fx equal to your 4x plus 3 upon 6x minus 4, right? And x is not equal to 2 by 3, and show that FOF of x is equal to x for all x not equal to 2 by 3. And what is the inverse of f? So fx is your this function, you can see it is not defined for 2 by 3, right? Now f of x is f of fx, like f of this complete term. Okay. Now in place of your x in fx, put 4x plus 3 upon 6x, like here it is plus 3, okay, plus 6 times this complete f and minus 4, right? Now replacing this we got by replacing x by 4x plus 3 upon 6x minus 4 in the original fx. Okay. So multiply, you have to take the LCM, and when it is solved you'll get it as x, which means it is the identity function of x, right? For all x not equal to 2 by 3. So that means FOF is your I of a. Okay. So where a is, who is a? A is your r minus 2 by 3, which is your domain of the function. So that means f inverse is f itself. State with reason whether the following functions have inverse. Now find the inverse if it exists. F is mapping from 1, 2, 3, 4 to 10. And it is like 110, 210, 310, 410. Now you can clearly see that f1, f2, f3, f4 have image 10. So this function is many 1 instead of being 1, 1. So definitely it has no inverse. Second is G 5, 6, 7, 8, 2, 1, 2, 3, 4. Like G is defined here as 5, 4, 6, 3, 7, 4, 8, 2. Like, so see, observe this 5, 4 and 7, 4. Right? So what is there? That G of 5 and G of 7 is 4. So means it is again a many-one function instead of being 1, 1. So inverse does not exist. The third part is H is mapping from 2, 3, 4, 5 to 7, 9, 11, 13. And at 2 it is 7, at 3 it is 9. See from here, at 4 it is 11, at 5 it is 13. So we get distinct elements of the domain have distinct images under H. So means function is clearly 1, 1. Now see the range. Range is the set of second elements in these ordered pairs. Okay. So which is your 7, 9, 11, 13, and it is equal to this codomain. Okay. So when range is equal to codomain means the function is onto. And definitely when function is 1, 1 and onto, so it has inverse. And inverse is given by, see here, it is 2, 7. So it will be like 7, 2, 3, 9. So it is 9, 3, 11, 4, 13, 5. Number 6 is show that f is mapping from -1 to 1 close interval to R. given by fx equal to x upon x plus 2 is 1, 1, right? Find the inverse of the function f mapping from -1 to 1 to range of f. So you know how to prove 1, 1. I have to take the two elements in my domain. Domain is my closed interval -1, 1, and such that f of x1 equal to f of x2, which I'll get by replacing this my x by x1 and x2, right, in this function. So x1 upon x1 plus 2 equal to x2 upon x plus 2 plus 2. Now I'll cross multiply this to get my next result. So after cross multiplying and cancellation, I'll get 2x1 equal to 2x2 means x1 equal to x2 means function is my 1, 1. Now we have to find the inverse of the function, right? So that means range of the function. Here is your, see, the range of the function is, your range of function is equal to the codomain. Okay, it is equal to the codomain. That means function is behaving onto also, right? Range is equal to the codomain, right? So means this is the condition for ontoness. So function is both 1, 1 and onto, therefore it is having its inverse. And y is equal to fx implies x equal to f inverse y. Now how to find f inverse? Let's express first your x in terms of y. So y equal to x upon x plus 2, cross multiply, and I'll get from here x as 2y upon 1 minus y. And it exists only when y is not equal to 1, because otherwise it becomes undefined, right? Now from 1 and 2, what will I get? F inverse is mapping from y to x. It is defined by f inverse y is equal to x, right? F inverse y equal to x, and x is your 2y upon 1 minus 1, okay? And y is not equal to 1. Number 7 is consider f mapping from R to R given by fx equal to 4x plus 3. Show that it is invertible. Invertible means I have to show the 1, 1ness and ontoness, and then find the inverse. So f is mapping from R to R given by fx equal to 4x plus 3. So it will be invertible if and only if it is 1, 1 and onto. So take x1, x2 belongs to the domain of R such that f of x1 equal to f of x2, that is 4x1 plus 3 equal to 4x2 plus 3. So it gives me x1 equal to x2. For ontoness, let y belongs to the codomain of this codomain R, okay, the codomain R, such that y equal to fx equal to 4x plus 3. So now I have to express x in terms of y. So I'll get x as y minus 3 by 4, right? So take fx and in place of x put this value, and this turns as 4 times y minus 3 upon 4. This will get cancelled, and I'll get it as your y minus 3 plus 3, which again gives me y. So that means every y is fx, that is codomain equal to range. So that means function becomes onto. So it is both 1, 1 and onto, and hence f inverse exists, right? So therefore fx equal to y, that is f inverse y equal to x, that is f inverse y is, who is x here? X is y minus 3 upon 4. Number 8 is consider f is a function mapping from R positive to semi-closed 4 infinity given by fx equal to x square plus 4. Show that f is invertible, and f inverse given by f inverse y equal to root y minus 4, where R plus is the set of all non-negative real numbers. So let us start. This is the given function, okay? So it will be invertible if it is 1, 1 and onto. So for 1, 1, let x1, x2 belongs to the domain, that is R positive, such that fx1 equal to f of x2, that is your x1 square plus 4 equal to x2 square plus 4, which gives me x1 equal to plus minus x2. Now you know I have to reject the negative sign as x1, x2 belongs to R positive. So that means I get x1 equal to x2, so that means f is 1, 1. And you know we did earlier questions also in which your, if it is the set of all real numbers, then it will not be 1, 1. Now let us check the ontoness. So let y belongs to the codomain 4 infinity, then y is equal to fx, which is your x square plus 4. Now you have to express x in terms of y. So I'll get y minus 4 equal to x square. X square equal to y minus 4, which is equal to plus minus root y minus 4. So again x is you are belonging to R positive, so I'll reject the negative sign, and x is your root y minus 4. So that means x equal to root y minus 4 equal to R positive. It is belonging to R positive because for all y belonging to codomain 4 infinity, how is this y minus 4? It is always positive, right? And hence this root y minus 4 belongs to R positive. Now take x equal to root y minus 4 and put it here in fx in place of x. So I get root y minus 4 whole square plus 4, and this gets cancelled with this and we get y. So that means every y equal to fx, that is codomain, is equal to the range. So that means my function is onto also, and f inverse exists, right? So f inverse exists, and how will we give it? That fx equal to y, that implies my f inverse y is equal to x. F inverse y equal to x. So that means your f inverse y, who is x here? Can you see the x? X is your this root y minus 4, right? So this is my f inverse y. Okay. Number 9 is consider f mapping from R positive to minus 5 infinity semi-closed and fx equal to 9x square plus 6x minus 5. Show that f is invertible with f inverse y equal to root y plus 6 minus 1 upon 3. So f is mapping from R positive to minus 5 infinity semi-closed. This is function. So now definitely it will be invertible if it is both 1, 1 and 1, 2. So for 1, 1, what do I do? Let x1, x2 belongs to my domain R positive such that f of x1 equal to f of x2. That means my 9x1 square plus 6x1 minus 5 equal to 9x2 square plus 6x2 minus 5. Now bring everything to this side. You know minus 5 and 5, minus 5 will be cancelled. So take 9 common from these first two. 9 times x1 square minus x2 square plus 6 times x1 minus x2 equal to 0. Now it is a square minus b square as a plus b to a minus b. From these two take x1 minus x2 common, right? And it becomes 9 times x1 plus x2 plus 6. Okay. Now see from here that this 9 times x1 plus x2 plus 6 is always positive and is not equal to 0. Why? Because my x1, x2 are positive. So some positive plus 6 will be positive, greater than 0, right? So that means definitely the other factor x1 minus x2 is 0. That means x1 equal to x2. That means my function is 1, 1. Okay. And now let's prove it as onto. So let y belongs to the codomain semi-closed interval minus 5 to infinity. So for it, let y is equal to fx equal to 9x square plus 6x minus 5. So let us express x in terms of y, and here you will use the method of completing square. So take 9 common, right? So this will become like this. Okay, reduce this becomes 3 to the 6, 3 is the 9. Now adding and subtracting half of coefficient of x whole square, right? So that means half of coefficient of x is 2 by 3, so which is 1 by 3 whole square. So I'll add and subtract this like 1 by 3 whole square and minus 1 by 9. So this turns to x plus 1 by 3 whole square and it is minus 6 by 9. So that means it is 9 times, open the brackets, 9 times x plus 1 by 3 whole square minus 6. Okay. So y plus 6 equal to 9 times x plus 1 by 3 whole square. Right. So this becomes your y plus 6 upon 9. So x plus 1 by 3 is equal to plus minus root of this y plus 6 upon 9. So x is minus 1 by 3 plus minus root y plus 6 upon 3, that is minus 1 plus minus root y plus 6 upon 3, right? Now I have to reject the negative sign. Why? Because I have to reject the negative sign, as you see that this negative term means if I'll take this both negative signs, right? So this result will not be belonging to R positive. Okay. So that means I should take this minus 1 plus root y plus 6 upon 3, which will be belonging to R positive, right? For every y belonging to codomain minus 5 to infinity, right? Also now I have to take fx equal to this 9x square plus 6x minus 5, right? Now put the value of x taken from here in this equation, and this expression changes to y. Okay, that means we get y is equal to whenever y equal to fx, we get fx equal to y. That means codomain equal to range. Range is equal to codomain, right? So f becomes onto. So that means inverse exists, right? So how inverse exists? We take that if y equal to fx, then f inverse y equal to x. So that means f inverse y is your, this is my x, this one, this x I will take. Okay. So that means you can rearrange it to write root y plus 6 minus 1 upon 3. Number 10 is let f mapping from x to y is an invertible function, then f has unique inverse, right? So see that since f is mapping from x to y is an invertible function, therefore definitely the function is having a inverse. Okay. Now again, because f is mapping from x to y is invertible, therefore it is definitely 1, 1 and on 2. That means what is the meaning? That for every y belonging to y, there exists unique x belonging to x such that fx equal to y. Okay. So if possible, let g1 is mapping from y to x, means I'm considering two different inverses, and at last I'll prove that both of them are equal. So let g1 is mapping from y to x, g2 is also mapping from y to x. Two different inverses of f are there. So that means g1 y is equal to x and g2 y equal to x again. Now let us take g1 of, right, which is equal to ix, and fo g1 which is equal to iy. Also g2 of will be equal to ix and fo g2 will be equal to iy, right, by the definition of inverse. Okay. Now for all y belonging to y, this g1 y equal to g1 fx, right? G1 of y is equal to g1 fx. Why? Because y is equal to fx, right? So it becomes by 1. What does it become? g1 of x is equal to your ix of x. Okay. See from here. Okay. And which is equal to g2 fx, which is equal to g2 y by equation number 1. Okay. So that means what happens, that g1 y is equal to g2 y for all y belonging to y. So ultimately these g1 and g2 becomes equal. They are equal by the definition of equal functions. So that means if inverse is existing, then it is unique. Question number 11 is, consider f function mapping from 1 to 3 to ABC given by f of 1 is A, f of 2 is B, f of 3 is C. Find f inverse and show that f inverse whole inverse equal to f. So a function is given a map from 1 to 3 to set A, right? That means ABC, okay, which is your set B here. 1 to 3 is your set A and ABC is set B, right? So such that f of 1 is A, f of 2 is B and f of 3 is C. So you can see it is represented by arrow diagram. So this is your A, 1, 2, 3 and this is your B, which is your ABC, right? So as you can see that f of 1 here is A, f of 2 is B, f of 3 is C. So clearly f is 1, 1 because distinct elements of A have distinct images in B, right? And also you can see that A, B, C all means all elements of B have your pre-images, right? And also the range is equal to the codomain here. Okay, so range is equal to codomain, so that means the function is onto here also. So that means you know that f inverse exists and f inverse is a map from B to A. Okay, right? So what will be f inverse A? F inverse A is 1, f inverse B is 2 and f inverse C is 3. Out. So again by the definition of inverse of function, what will be having? F inverse is a map from A to B and f inverse whole inverse of 1 will be again when we will take it, it will again be from this to A. Okay, and f inverse whole inverse 2 will be B and f inverse whole inverse 3 will be C. So that means by definition of equal functions from this equation number 3 and 1, what we will be having? We will be having our f inverse whole inverse equal to f, right? So note down that two functions f and g are said to be equal if they have same domain, right? And fx equal to gx for all x in their common domain, right? So this is the way how we will prove this question. Number 12 is let f is mapping from x to y is an invertible function, then inverse of f inverse is f and f inverse whole inverse equal to f, right? So this is also a question given here, which we need to prove, like f is mapping from x to y is invertible. Therefore, there exists a function g which is equal to f inverse mapping from y to x, such that gy equal to x, where f of x is y, right? So we'll apply the identity function method. So also g of f is equal to ix and f of g equal to iy. You know, this condition holds when the function is invertible. Now f is invertible, that means it is clearly 1, 1 and onto. And g, the inverse of f, which is also 1, 1 and onto. So that means g is also invertible. That means g inverse exists and it will be a map from x to y. Now from 1 we have also f is inverse of g. So that means f equal to g inverse. Now putting g is equal to f inverse, what we will have, this will be f inverse whole inverse. So that means f inverse whole inverse will be equal to f. So this is how we'll prove this question. Question number 13 is f mapping from R to R, given by the function fx equal to 3 minus x cube raised to power 1 by 3. You have to find f of fx. Okay, so out of these 4 options, one is true. So here the function is mapping from R to R. Function is given by 3 minus x cube raised to power 1 by 3. So I have to find f of x, so which is f of fx. So in place of fx, you have the function 3 minus x cube raised to power 1 by 3. So which is of the form like ft, where t is your 3 minus x cube raised to power 1 by 3, right? So means it becomes of the form of 3 minus t cube raised to power 1 by 3, right? So now I have to put the value of t as this, right, by equation number 1. So I'll get it, my function 3 minus x cube raised to power 1 by 3, right? So after opening it, you will get that 3 and 3 will get cancelled and I'll get it as just x. So option number C is my correct answer. So it's an easy question. Number 14 is, let f is mapping from r minus 4 by 3 to r be a function defined by fx equal to 4x upon 3x plus 4. The inverse of f is the map g from a range of f to this your r minus 4 by 3, given by, you have to find the inverse. Okay, so given you have fx is 4x upon 3x plus 4, so inverse of f is g, right? So that means that function is 1, 1 and onto. That's why the inverse is existing. And y is equal to fx equal to 4x upon 3x plus 4, right? So then what we do, we have to, when the function is 1, 1 and onto, how do we compute the inverse? We express x in terms of y, right? For it, cross multiply, right? And you will get your x as 4y upon 4 minus 3y, which is your f inverse y, right? Because if y is equal to fx, then x equal to f inverse y. And because g is equal to f inverse, so this your 4y upon 4 minus 3y. So that means g of y will be 4y upon 4 minus 3y. So that means option number B is my correct answer. So this was all regarding your exercise 1.3. I hope whatever is taught to you is clear. Please give it a good round of practice and the things will be clear to you. Thank you so much.